last but not least, Professor Chaim Eshed. Chaim was the first one to head, and still heading, the space office in the Ministry of Defense, the space program in the Ministry of Defense. He is also professor in the Technion, and also sitting in the board of the space agency. Where is he? Chaim, please, come.
Good afternoon. I promise there'll be no slides, no formulas, no black holes, just ideas that I want to discuss with you. You can also hear my sore throat, so I'll make it short. So as Professor Ben Israel said, I have been heading the military space for the last 33 years. We achieved some impressive results. We launched like 15 missions. We have remote sensing satellites, communication satellites, and they spread in all the spectrum, and of course I cannot enter into details. But what I wanted to discuss with you is that we are now on the verge of a national space program that, as you heard from Professor Ben Israel, the Prime Minister agreed to go on it. And the question is, what direction is Israel going to take? You know that Israel excels in high tech. It also excels in UAVs, unattended aerial vehicles. And maybe you know it's only the US, and Israel is next to the US in the whole world in UAVs, and I was lucky enough to start this project. So we think that space in Israel can be a center of excellence. And I have two remarks before I present the question of present and future technologies that we have to pick up. First of all, space today is still considered to be extraordinary, exotic, and beyond the reach of many nations and people. And also limited budgets of national security activities and economical crisis force defense agencies to rely heavily on outsourcing and commercial dual-use services. This includes also science and technology. As you are well aware, military space is also science and technology. And second remark is, in my view, if benefits of space are clear into the lives of ordinary citizens, the public will be more receptive to expanded budgets for space exploration, also for science and technology, and then I will not have to find the treasury to get what the Prime Minister promised us. And now to the main subject. And I hope I'm not offending Laurie or David with their wonderful presentations. The space age started more than 50 years ago. It achieved some remarkable results relatively in a very short period of time, such as, for example, the capability to communicate in a digitized wideband through space. This allows, of course, business transactions all over the world in no time, and it keeps the pulse of modern life the way it is today. And these capabilities are indispensable and are taken, unfortunately, for granted. But we have to admit that national defense needs, like the space race between the US and the former Soviet Union, allowed a big investment in space science and technology. And this accelerated space, and the same reasoning It applies to the huge investments in the SDI, if you still remember, that's the Strategic Defense Initiative in Reagan's and Bush administration. And the fact is that the Soviets couldn't keep up with the U.S. investment, and maybe that was the last straw that caused the collapse. But since the SDI, most of the budgets were chopped, and they are much lower than what we expected. So there is a general feeling, and I'm speaking after talking with my colleagues in Goddard Space Flight Center, or in Kourou, or in ESA. There is a general feeling that besides the achievements of the Apollo program, and since the termination of the Cold War between the US and the former Soviet Union, most innovative thinking in space technologies was stopped more or less. We've seen beautiful slides, but in our view, in my colleagues' view, it's only linear sort of thinking. So what we think, and we thought in Israel Space Agency, okay, what direction do we take? So in our view, focusing on solution of several basic problems. You see, Israeli military space succeeded by focusing. That's the formula. So by focusing on maybe 3 or 4 basic problems, we can advance space exponentially. One of the basic problems that we observe is the high cost, that's tens of thousands of dollars, for launching every kilogram of hardware into space. That is still true with SpaceX, very successful launch, and we are in touch with them, but that's not still it. We have to go down one order of magnitude. So that's one problem. Another problem is the very high cost of space-qualified components. You know, the price sometimes can go 100-fold. And the third problem that we pinpointed is that is very significant in the last couple of years is the big overruns in budgets and timetables. In most of the space projects, we were getting bigger and bigger. And maybe one reason is the natural tendency of engineers to load too many functions on a single craft, or maybe the conservative minimum risk approach in case of a failure. So out-of-the-box thinking and concentrating may change this attitude and make getting to space much easier. So in order to lower the cost of space projects and make space science and technology more accessible, we can choose one of the following approaches. And I'll tell you what we decided in the meantime. The first approach is to adopt the vector of smaller and smaller spacecraft. That is, go to micro, which is 100 kilograms. You know that our military spacecraft are around 400 kilograms. And they are considered to be very small. But we decided we can get more or less the same results with microsatellite, which is up to 100 kilograms, and then go to nano, 10 kilograms, go to pico, 1 kilogram satellite. And believe me, there are 2 more lower scales down to 10 grams. And we are working on these items at the Technion Research Institute, and tomorrow I will elaborate on it. So that is one way to go, to adopt existing technologies and nanoelectronics, nanomaterials, NEMS, nano-electromechanical sensors that are the size of atoms, and on. So we will focus on technologies that can reduce weight and increase performance in space. This way, the weight of the launch and the cost will go down drastically. But then, of course, we have some missions that will need some optics with bigger apertures and antennas for deep space missions. So then we'll have to develop the swarms of satellites, and on this we also invest a lot. One of the examples of this approach is DARPA's R&D project F6 and the civilian European FP7 that I will describe later on. So that was first approach that we thought it's simpler for Israel with this smaller budget, but now that we're going to a national program, we have to think twice. So the second approach is to try and focus on bigger satellite, but develop special light materials. I know we've been working on nanomaterials for many years, but it was only seed money. If we want to focus, we can create nanotubes that finally, let's say in a decade, can make the basic elevator to space, which means we will not have to launch a rocket. So we didn't focus on this issue, so that's something that I propose to go for, and also go to gossamer materials that can create in space huge antennas and huge optical aperture. I'm speaking about hundreds of meters optical and tens of kilometers antennas aperture. And also use fractionated space so that information exchange will replace structures. It means you have all the subunits and information or virtual structure can hold them together, and we are performing work on all one of these subjects. So this way, big structure in space will be replaced by information and exact location. Another problem, that will be the last one that I will specify, that we have to focus on is to develop higher energy density propellants. That's also not much thinking was done on this problem. And finally, try to replace chemical fuel by electron and ion propulsion, and I will not elaborate on it. And finally, we might get to plasma that will propel spacecraft into space. So let's get back to Israel, and what is Israel to do? So Israel is by definition a small country with small budget allocated to space and technology. Unfortunately, everything that was done until now in the last 33 years came from defense budget, and this shouldn't continue anymore because basic research and applied research have to come from the government, and that's why the Prime Minister agreed to go on this project, but we still have the Treasury, which is not a simple problem. Maybe it's the fourth problem. So we adopted the micro-miniaturization approach in our civilian and dual use, and at the beginning of our national program that was based on extensive survey. We looked what other agencies did in the world and how well are we compared to them. So I'll give only short examples. The first example that we have of shifting from heavy and expensive mission to smaller satellite is the Clementine satellite. That was developed by the US BMDO, the Ballistic Missile Defense Office. Its mission was to explore and map the moon, but also, and that's important, to integrate in it advanced miniaturized sensors that, by the way, we have also developed. We specialized in this in the Technion, and several advanced technologies for small satellite, the so-called, if you remember, the brilliant pebbles, in the Star Wars scenario. So the weight of the satellite was only around 200 kilograms, and the total cost of the mission was under $75 million. Would you believe it? And that was for a very complex and successful mission. The second small satellite example is the Canadian microsat MOST, that stands for Microgravity and Oscillation of Stars. It weighs only 50 kilograms. It was launched in 2003, and it is the smallest size of a suitcase, astronomical telescope. That's why it's called the Hubble telescope, with a pointing accuracy of 1 arc second at the cost of only $6 million. And the last example, and that's for Lori, it's NASA's Minisat robotic spacecraft mission, the New Horizon that you mentioned, en route to dwarf planet Pluto, only 39 astronomical units away. Its size is dictated by a 2-meter dish antenna at a frequency of 8 gigahertz, transmitting only 12 watts. 12 watts from a distance of 6 billion kilometers. So as we heard, it will get to Pluto in 2015, and we are all hoping for a success. We can also mention DARPA's R&D, which I said I will elaborate on it. The F6 is for Future Fast, Flexible, Free-Flying, Fractionated Spacecraft, and we are trying to develop every aspect of this, and we also propose the American DoD and NG and NGA, and I hope there'll be a joint venture. All these examples show that we can extend the capabilities of micros and smaller satellites to other units of performance and also use them in coherent swarms for bigger apertures need. So if we turn now to what is needed in our view in future technologies to make space more accessible, we can mark down the following, and I'll do it shortly. First of all, lightweight spacecraft, so which means investing in nano, but not the way of seed money that we invest much more, make a bigger effort, team up, and cross this border and get finally the space elevator. And low-cost launches implies focusing on high energy density propulsion, which that again, the number of research works on this subject are not very big. And also customer off-the-shelf space components to use in space environment means simpler and cheaper qualification processes. And finally, big number of very small as well as very large lightweight spacecraft that will be flexible to create many coherent functions by command from the ground. That is, in my words, big functions performed by swarm of cooperating small elements. So Israel can contribute also to scientific missions and space exploration that look very attractive and challenging. In the micro region, I'll mention the 7th European Framework Program, FP7, by Dr. Noach Bosch. I hope he's somewhere here. He is the coordinator, and 12 other European partners that go with it. And the proposal is not meteor and thunderstorm research satellite. It's based on a train of 3 nanosatellites. They'll be injected on the same orbit without correction in a single launch. So this mission will perform meteor, lightning, and sprite observations above the atmosphere. In addition to its high scientific value, it will facilitate access to space for smaller scale research mission in the future, and later on you'll see some example what we can do with the nano. So the last one, in the bigger science mission, I'll mention NASA's Space Science Vision mission, that is the Interstellar Probe, which to me looks very appealing because that's huge science, huge obstacles, and we've got to take something which the world will look after. What we're doing is all linear, and I think we should do here something out of the box and try to join this project. And I think that our scientist community in space, which is very distinctive in the world, especially in Tel Aviv University and the Hebrew University of Jerusalem, can contribute a lot in such a joint venture. So I'll summarize. I see I'm running out of time. In view of the smaller budgets allocated everywhere to space, what is needed, in my opinion, is to join and team up on mutually agreed problems, and I've placed 4 problems that if we solve them, access to space will be much better. This will leverage present and future into making space science and technology to develop much faster and space access to be much simpler for the benefit of humanity that was mentioned, and I do believe that our future is in space. Thank you.